Hello and good afternoon, everyone. Thank you for joining us this afternoon for the first webinar on this 5-webinar series for Project LAMP that we will be presenting to all of you this spring and summer semesters. My name is Jorge Reyes, and I am the project coordinator for Project LAMP. Project LAMP is a USDA NIFA sponsored project under the name Optimizing the Cost Effectiveness of Lighting and Control Environment Agriculture. And through this project LAMP, our team is helping growers get more value out of their lighting system by providing horticultural and economical information, tools to manage lighting for optimal crop growth and quality, and of course, to maximize the return on investment. Without further ado, and without any more details, let me introduce to you to our first speaker of our first webinar of the series. You will meet Dr. Neil Mattson. Dr. Neil Mattson is a professor in the School of Integrative Plant Science at Cornell University. He's got research, extension, and teaching appointments in his position at Cornell. His research program focuses on understanding the influence of environmental factors and cultural practices on the physiology and development of floriculture crops. His extension efforts are directed toward greenhouse extension programming, and his goals are to deliver pertinent research-based information to greenhouse growers to help them make sound management decisions. And of course, he also teaches hydroponic food crop production and management at Cornell every other year. Dr. Mattson is also the director of Cornell's Control Environment Agriculture Group, and in Project LAMP, he is developing light intensity and quality strategies to improve quality and reduce crop time of flower and vegetable transplant. Dr. Mattson is also the lead of the outreach team for Project LAMP. Dr. Mattson, the room is all yours.
Thank you so much, Jorge. Let me share my screen. Okay, we'll begin. So we'll talk about a bunch of different online tools that are available from Project LAMP that can help growers as well as researchers make decisions with the lights that they implement. And just a little bit about Project LAMP. Project LAMP was a multi-institutional, multi-year project that was originally developed through Mark Van Eersel. And we refer to him as our leader in memoriam now that he's passed away. And Mark really saw a need back then, this goes back 5+ years ago, to look at, take a step back at supplemental lighting in greenhouses or sole source lighting in indoor farms. And besides asking what is the right type of light for my facility, whether that be LEDs or HPS, is we also need to understand how crops respond to light and where it's economical to add supplemental light or add additional light. And so the project has brought together engineers and horticulturalists and economists and other specialists that have looked at different ways of sensing plant responses and controlling light and understanding how plants respond to light. Our current leader now is Dr. Renito Farazi at the University of Georgia, and we continue on. And I have my own story with Mark that I wanted to share. So I've known Mark for 15+ years as a faculty member, and relatively early in my career, I was happy when Mark reached out to me to ask if we would be interested in writing a review paper together. That one was actually on strategies to fertilize crops efficiently. And so we went ahead and wrote this manuscript and submitted it. And one of the reviews came back, and we often get these reviews that find all these picky details, and we go back and change them in papers. But one of the reviews said that this was the worst review paper that they had ever read. And they didn't provide very constructive criticism. And I remember feeling kind of downtrodden, and forwarded that to Mark. And his first response was, it seemed like most of the suggestions were pretty minor, except for reviewer number 3, who seems to recommend a public burning of the manuscript and all computers used to prepare it. But we should probably ignore that suggestion. And indeed, we did. That gave me the encouragement I needed to revise the paper and resubmit it. And indeed, it was accepted. And then when it was accepted, Mark said, perhaps we should add an acknowledgement to the manuscript. We thank 3 of the 4 reviewers for their constructive criticism. So to me, that was just a great example of Mark's kind of dry sense of humor and matter-of-factness, but also his way of encouraging both new faculty members in terms of myself, but the graduate students that he interacted with as well. So, okay, we'll dive into lighting. And what I want to do is start out with just a reminder of the units or the terms that we use to talk about lighting for plants. And some of the terms that are used, like the energy efficacy or the light output of fixtures, because those things are going to come in handy when I then talk about these lighting calculator tools. So if we look at what the sunlight gives us, it's very broad spectrum light, and this is the graph on the left. So we have on the x-axis is what is the wavelength of light in nanometers, and then we have the relative intensity on the y-axis. So the sunlight gives us below 400 nanometers. That's referred to as ultraviolet radiation. And then we get all the colors of the rainbow from 400 to 700 nanometers. So we get the violet to blue to green to yellow to orange to red. And then past red, we get far red radiation that we're increasingly learning is important for plants for signaling how they grow. And then long wave radiation past that could be felt by the plant in terms of heat or warmth, for example. And so we'll show you in a second how plants perceive light, but how humans perceive light. So this is what we have, which is the graph on the right. We do see all of the colors of the rainbow from purple to red. However, our eyes are really attuned to see these mid-range wavelengths, so green and bright yellow and bright light blue. Those are the types of colors we see very well. And then we're not good at seeing red or blue in terms of the relative intensity. So it turns out that our eyes are not a very good way of kind of quantifying light. We also detect light at very low levels. We can read and see perfectly well, but plants need much higher amounts of light to drive photosynthesis, which is their energy source. So in terms of lighting, we have this unit, which is called photosynthetically active radiation, and it's all the light between 400 and 700 nanometers. And where this comes from is McCree, and there's been other people that have done this work, but they exposed plants to different wavelengths of light, and then they looked at how they responded in terms of photosynthesis. And so in this work by Keith McCree, there was actually a little bit of photosynthesis with ultraviolet light, but then most photosynthesis happens between 400 and 700 nanometers with a small peak at blue, a little bit of a dip in green. And actually, if plant leaves look green to our eyes, and it's not because they reflect all green light or don't use green light, but they do differentially reflect more green light, more green than other colors. So they do use green for photosynthesis, just not quite as effectively as blue. And then at red, we get a nice peak in photosynthesis as well. To make things easier, plant scientists decided a long time ago is that we would consider all of those wavelengths equally between 400 and 700 nanometer. And the unit that we use is micromoles per meter squared per second. And a micromole is just a very large number. A mole is 6 times 10 to the 23rd. We use that term in chemistry. So a mole of hydrogen atoms weighs 1 gram, for example. In this case, so it's a micromole is 6 times 10 to the 17th. So that's lots of particles of light that hit a square meter per second. And that's the unit that we use for plant lighting. And then the light integral, or the daily light integral, is the accumulation of all of the light that's received in a day. So then an hour has 3,600 seconds, and then a day has 24 hours. And by the time that we get to that daily light integral, there's, of course, then more particles of light than there are in a second. So then we use the term mole, which is 6 times 10 to the 23rd. So when we talk about light targets for plants, the DLI is in moles per meter squared per day. And so you measure plant light with what are called quantum sensors, and they usually cost about $300 up to $1,000 for really nice, fancy ones. And they will show you then all of that light between 400 and 700 nanometers. You can get handheld ones like the one on the right, or you can get ones that you connect with data loggers. I like this one on the bottom that it's actually a little meter that you can place in a spot, and it will log and record light that it receives every day for several days. So ultimately, if we want to convert between instantaneous light, which is the intensity of light that we measure at 1 second in time, to daily light integral, the math is actually pretty easy. We just need to multiply times the number of seconds in an hour times the number of hours, and then divide that by 1,000,000 micromoles per mole. So in this example, if let's say we have a high pressure sodium fixture and it gives us, in terms of instantaneous light, 200 micromoles per meter squared per second, how much light will it supply if that's kept on for 12 hours? And so we just multiply 200 micromoles per meter squared per second times 3,600 seconds per hour times 12 hours. And then we divide that by 1,000,000 micromoles per mole. And that tells us that we get 8.64 moles per meter squared per day. So sunlight, if we're growing in a greenhouse, gives us a lot of light. However, it can be really variable according to the year, at least if you're in a cloudy location like I am in upstate New York. And I love showing this graph. This was made by Lou Albright at Cornell across a 14-year period of time. So each of these dots represents the daily light integral for one day. And then we have day of the year, which starts at January 1st is day 1, and then December 31st is day 365. Or I guess in this year, 366, because it's a leap year. So the middle of the graph is the middle of summer. And so what we find is the maximum daily light integral we can get from the sun is 65 moles per meter squared per day. But the interesting thing is, at least in our location in New York, there's a lot of days that are cloudy in the summertime, and we will get 10 times less light than that. And then in the wintertime, the maximum amount of light we can get from the sun, because we have a shorter day length in the wintertime, is about 17 moles per meter squared per day. But if we look at kind of January and then December, we see that it's, for us, pretty rare to get those really high mole days. And more often we get, say, 1 to 5 to at most 7 moles per meter squared per day during the wintertime. And this is the amount of light that we get outdoors. But what actually gets into the greenhouse is about 45 to 70% of that, depending on the glazing that you have and the overhead or structural components that you have in the greenhouse. So a little bit more on lighting units. In the olden days, when LEDs were first developed, there were not kind of standardized lighting units that were used, and so it was hard to do like apples to apples comparisons of different fixtures. So in human lighting, we look at how many foot candles does a lamp put out, and so what we want to know in terms of horticultural lights is what is their light output in terms of photosynthetically active radiation. So nowadays, most LED fixtures, at least reputable horticultural LED fixtures, they're going to tell you a bunch of information, including the wattage that they use. The voltage tells you what kind of outlet you need or power source you need. Then we can learn about the red to far red ratio, how the light spectrum breaks down. So we have, in this case, 35 micromoles of the light is blue light, 78 micromoles is green light, and so on for red and far red. And then in terms of total light output from a fixture, what we look at is par flux. So that's the photosynthetically active radiation. And the unit here is micromoles per second. So this particular fixture outputs 191 micromoles of light per second. This doesn't tell us how that light is dispersed, but let's say if we could cover 1 square meter with that fixture, we would have an average of 191 micromoles per square meter per second in that case. And then another really important thing is looking at the light output divided by power consumption, we can calculate the efficacy. And the photosynthetically active radiation efficacy is a number that's in micromoles per joule, and higher means better. So higher means that we get more light output per unit of energy. And so with the conversion factor here, basically we just need to divide par flux by power. And then we have to know that a watt is 1 joule per second. So the math works out. So what have we learned about how LEDs have improved over time? So in terms of their energy use, or what we call the efficacy, the light output per joule of electricity, there was a paper that looked at 10 different high pressure sodium lights back in 1994. And the best ones gave us 0.98 micromoles per joule. And then that actually progressed over about 20 years. High pressure sodium lights improved in their efficacy and reached about 1.7 micromoles per joule in 2014. And since that time, they have plateaued. There's been maybe some small advancements, but these fixtures are 1,000-watt double-ended fixtures with electronic ballasts. And so I always like to tell growers, even without looking at LEDs, look at high-pressure sodium lights. And if your operation has 30-year-old high-pressure sodium lights, one, the bulb may be very old and dim, but also just by replacing your old HPS fixtures with new HPS fixtures, you can almost double their energy efficiency. So in 2014, actually, the best LEDs had the same efficacy as the best high-pressure sodium lights. However, LEDs since that time have rapidly improved, and they've really gained efficacy over time. So by 2016, they were about 40% better. And by 2021, we now have about double the efficacy or double the light output of LEDs back in 2014. So then the amount of energy that you can extract, or the amount of light that you can extract from electricity, is starting to plateau. So there's a theoretical maximum. So for a fixture that is 80% red and 20% blue, the maximum amount of micromoles per joule that we can get is just over 5. And current technology then is approaching 4. Or 3.7 or so, versus HPS is about 2 or a little bit less than 2 with no further gains expected. So we've grown a lot in terms of energy efficiency of LEDs, and then there's going to be some small gains that can be made, but those energy efficiency gains are slowing down at this point. And then it's interesting to look at, in terms of different colors of LEDs, how energy efficient are they? So it turns out that red is very energy efficient. So we can get about 4 micromoles per joule. That efficiency goes down a little bit with temperature of the fixture, which makes sense. And far red light actually has a little bit higher energy efficiency than red. Then blue is still pretty good, not quite as good as red, but it takes a little bit more energy to generate blue light. It's shorter wavelength light. It takes higher energy to generate it. And then white is not as energy efficient, but it's easier for our eyes to look at than like a red-blue fixture. So how we generate white LEDs is we actually start with a blue LED, a blue diode, and we coat that with a phosphor coating. That would be a coating that it ends up absorbing about 15% of the light, but then the rest of the light that it emits is across a broader wavelength range. So that kind of gives us all colors of the rainbow, which makes it look white to our eyes. And then the operating temperature of the fixture impacts how long these diodes can last and give out a good output. And so if we start with 100% light output, and our operating temperature is, this would be in degrees Celsius, I believe, 55 degrees Celsius. Those LEDs can be operated for about 50,000 hours and lose about 7% of their total output. If we don't have good temperature control on our fixtures, if they don't have a good heat sink or a fan, and our temperatures heat up, we can see that we can lose our operating hours very quickly. So at 105 degrees Celsius, something that would have operated for many thousands of hours now loses its output very quickly and will only operate for about 3,000 hours before it loses 5% of its output. Okay, so then before I get into these lighting calculator tools, just a little bit more on selecting lighting fixtures. And so in terms of the total quantity of light that we supply per unit of energy consumed, then where I was interested in that, that efficacy number, that micromoles per joule number. And then higher means we get more light output per unit of energy. Of course, another thing that we're thinking of is the initial cost. And so that's the number of dollars per fixture times the number of fixtures that we need to get a target daily light integral. Then we have the lifespan, which we need to think about. This is often reported as either Q70 or Q90. And what that refers to is, if we take Q90, for example, that means it's the number of hours that you can operate the fixture, and they dim a little bit over time, but the number of hours that you can operate the fixture to get, you've only lost 10% of total light output. So it's still operating at 90% light output. And this is important to think about because in like high pressure sodium lights, for example, maybe after about 5,000 to 10,000 hours of operation, we might want to change out the bulbs because they use the same amount of energy, but they have dropped in terms of how much light output they give us. So then for fixtures that have bulbs, we would think about the bulb replacement cost. For most LED fixtures, unfortunately, they don't have like bulbs or diodes that we can replace. We just have to throw away the whole unit. And then we think of the installation cost, the electrical capacity that we need to support that, the shading of the fixture. So if they're giving us greenhouse supplemental light, we don't want them to shade our plants to a large degree by having a large footprint to the fixture. And then you can work with the lighting manufacturers or lighting suppliers to design a lighting plan of how to place the fixtures in your greenhouse, like how many feet apart from each other to hang them or where to hang them from the rafters. And that will tell you the uniformity of the light plan and the instantaneous light output that you can get at crop canopy height. And then we won't go into it today, but other folks that work on Project LAMP have done quite a bit of work with the spectrum or the wavelength of light and the effects that that can have on plant quality. So in terms of some of these characteristics, like their energy efficacy and the Q90 and whether fixtures have warranties, a question that many growers ask is which LEDs meet energy efficiency and reliability criteria. And it's hard to know because there's a lot of different lighting products on the market. Well, luckily, there's a third-party nonprofit institute called the Design Lights Consortium. And they maintain a list of horticultural lighting qualified products list. So you can go to their website, designlights.org, go to horticultural lighting, and then you can search for registered LED fixtures that meet certain criteria. And these are designed for North America. And many energy efficiency programs, for example, some utility companies will help you adopt energy efficient LEDs by paying you some fraction of your upfront cost. But they often look for a fixture to be registered with the Design Lights Consortium to know that it's a suitable fixture. And then DLC revises their criteria every 2 years to become a little bit more rigorous over time. And here's an example of what you can find on their website. And let me back up for a second. Their current criteria is version 2.1. So the minimum efficacy that they're looking for is 1.9 micromoles per joule. That has to have a lifespan of at least 36,000 hours, which is the Q90. And it has to have a driver lifetime and a fan lifetime of at least 50,000 hours, and a warranty of the fixtures of at least 5 years. So you can go to designlights.org. I think nowadays, unfortunately, you have to register for a free login or free username, but then you can go through and search according to different metrics. Like you can be like, okay, show me all of the fixtures that qualify that are more than 3 micromoles per joule, or fixtures that have a given total brightness, the total photon flux, for example. And you'll get results back like this, for example. Okay, so then this information can help you find fixtures. And then once you have fixtures that you are looking at, or you might already have fixtures installed in your operation, then you're ready to use a bunch of the calculator tools that were developed by Project LAMP. And you can find these on our website, which is hortlamp.uga.edu. And then click on the LAMP lighting calculators. And you'll see a list of 6 different things, and we'll walk through a few of those different ones. So the first calculator that I want to talk about is called How Large Should My Lighting System Be? And so with this one, you're thinking of a greenhouse that doesn't have lights installed in it yet. And then you can select your background climate. So you can put in your zip code. And the software tool knows what is the average daily light integral that you get for every month of the year. And actually, it uses typical meteorological year data. So for every day of the year, it knows what a representative day looks like in terms of how much DLI you can get from the sun. And then you can input what percent of the days you want to be able to reach a given daily light integral target using a combination of sunlight and supplemental light. And then this calculator will tell you what the light intensity is that you need for a lighting installation. So let's walk through an example. And so first we would enter a greenhouse location. We'll look at Grand Rapids, Michigan in the case here. We'll put in the zip code so that it can pull in the climate data and tell us what the average sunlight is for each day of the year. And then we put in our electricity rate. So let's say 10.5 cents per kilowatt hour in this case. Then we put in some information about the greenhouse itself. So this is a gutter connect greenhouse that's 120 feet long by 180 feet wide. And then this transmissivity number, transmission percentage, is how much of sunlight actually gets into the greenhouse. So that's usually a number that varies from 45 to 70%. And you can make some guesses. However, the most accurate way to be able to plug in this number is to have a handheld light meter. And you can choose a bright sunny day without cloud cover, and go outdoors and measure how much light you get, and then go indoors several different representative points in the greenhouse and get an average reading of what light intensity is indoors, and then calculate the percent that gets into the greenhouse. So then in the next step, we enter what our target daily light integral is. So I guess here we're thinking of like head lettuce with 17 moles per meter squared per day. And then the lighting efficacy. So this is the number that comes from the fixture. So we're going to use a fixture that gives us 3 micromoles of output per joule. And then you can say what percent of days you want to reach the target daily light integral. So maybe ideally you'd have enough supplemental lighting so that you could reach the target daily light integral 100% of the days of the year. However, that's going to require a bigger lighting installation. And so if we could get away with, say, 90% of the days of the year, so that means in like December and January, for example, we're okay with not getting quite as much light and having slightly longer crop cycles, then we could get away with a lower lighting installation. So we're going to actually compare these two in one of our simulations. And then some crops require a dark period, like for tomatoes and peppers and other similar fruiting crops, we typically think of needing a 4 to 6 hour dark period. So in this case, I'm going to say that the lights could be on for up to 20 hours per day. And then a final feature or final point in terms of your electricity cost is that for commercial electrical rates, you're also paying a demand charge, which is based on the highest electrical usage that you have in a single 15-minute period during the month. And so $6 per kilowatt hour is a common demand charge. And it turns out that the demand charge can be up to about 40% of your electrical bill. So we wanted to capture that piece of information. All right, and then we click on the results. And so what we can see is, so in this case, we have the potential to use light or 100% of the light January through December. If you want to, you can go back and edit those separately. And you can say, for example, I'm not going to use light at all from April to September and see the effect that that has on your lighting costs or your ability to hit the DLI target. And then the graph shows us what the sunlight gives us in a typical meteorological year. So these blue dots are where the sunlight gave us, and this accounts for that transmissivity factor into the greenhouse. The blue dots show us where we got more than our target DLI, and it probably means we'd want to shade if we're growing like head lettuce on those days. And then the red dots show us where we did not, from sun, get the target daily light integral. And then the graph on the light adds up or tells us the amount of supplemental light that we need to complement the sun. And so we see many of these days in the middle of summer, for example, when we need 0 moles of supplemental light because we have enough sunlight. And then these blue dots show us where the days that we need supplemental light. And then the red dots in this case show us days where we can't, with this lighting installation, we can't achieve that 17 mole target. So in this case, this was saying that I want to hit my target 90% of the days of the year. And so it calculated that I need a 176 micromoles per meter squared per second fixture lighting output. And then that for operating that for 20 hours a day can give me up to 12.7 moles per meter squared per day. Then it tells us the cost of that lighting, so the electricity cost in terms of dollars per year, either per acre or for the designed footprint that I specified, that 120 foot by 180 foot, as well as the demand cost. And so I did a run where we looked at having 100 higher lighting installation that allows us to meet the daily light integral target 100% of the days of the year. And so our lighting costs per acre do go up slightly versus the left, which is meeting it 90% of the days of the year. So if I wanted to meet my lighting target 100% of the days of the year, I would need to have a lighting installation with 223 micromoles per meter squared per second, which can over 20 hours give me 16 moles of light per meter squared per day. So achieving that 100% DLI target means that I need a lighting installation that's about 27% larger than if I only hit that 90% of the days of a year. Okay, so that was one of the calculator tools. Another one, which we think of as kind of the opposite of this one, is how often will I reach my target daily light integral? And so this calculator works well if you have an existing lighting system, and you know what its output is in terms of what is the micromoles per meter squared per second that you get at crop canopy level. And so this one works very similar in terms of the inputs that you have. So I'm going to be in a greenhouse in Grand Forks, North Dakota. I have a little bit cheaper electricity rate. And then this is a greenhouse that's 30 feet by 96 feet. I have 55% greenhouse transmissivity. Let's say I'm growing tomatoes. So I have a target minimum daily light integral of 20 moles per meter squared per day. I have lighting fixtures with an efficacy of 3 micromoles per joule and a supplemental lighting capacity of 175 micromoles per meter squared per second. And then let's say because I have tomatoes that I can only have them on for up to 18 hours per day. So I need to have a 6-hour dark period. And so then you can hit submit. And you can get information like this one that tells us how much light we get from the sun. And then on the right side, what our supplemental light conditions are. And so it tells us with our current lighting installation, we can hit our daily light integral target 239 days of the year. And then we have the cost of that lighting per acre or for the design footprint of the greenhouse. And we know that we can get up to 11.34 moles per meter squared per day from our supplemental lighting system that has those specifications. All right, then I think the last calculator tool that I want to show us is one that I created. And this one's a downloadable spreadsheet, or I guess nowadays it's an online spreadsheet, which will estimate the number of fixtures that you need for your greenhouse or your lit space. And so in this case, we fill in things that are in the yellow highlighted boxes. So we know that the target instantaneous light intensity of our crops, let's say 200 micromoles per meter squared per second. Some information from the lighting manufacturer, so the lamp power consumption and the photosynthetic efficacy, the micromoles per joule. Then we have the area that we're lighting. So this is 1 acre, 43,560 square feet. You can choose to add a factor to account for light loss from edge effects. So in these lighting installations, there is some light loss to the edges. If you have, say, a very rectangular shaped greenhouse with a lot of perimeter space, you might have higher light loss from the edges. Then the number of hours that the lights are on per year, and our cost of electricity, and then the cost of an individual fixture. And then what it will calculate is, it tells us the area that we're lighting, which is an acre or 4,000 square meters in this case. It tells us that without accounting for edge effects, I would need 413 of these lighting fixtures for my 1 acre greenhouse. Based on the total cost of each fixture, that works out to a capital cost of $160,000. And then for those to operate for 2,000 hours per year, those are on for, or those use about 1 million kilowatt hours of electricity. So then we can calculate the electricity cost in dollars per square foot per year or dollars per square meter per year. And this tool could be really nice for comparing different fixtures to each other. So if you want to look at, like, should I adopt a more energy efficient LED? However, it has a higher capital cost. So you could put in like an HPS specifications into the lamp 1 tab, and then LED specifications into the lamp 2 tab. And then you can look at a simple payback calculation. So let's say we have a HPS fixture, which is cheaper up front, but has lower energy efficiency. And then compared to the second lamp, that's an LED, the LED has higher energy efficiency, but higher upfront cost. And then let's look at 2 scenarios, an electricity cost at 8 cents per kilowatt hour versus an area of the country like New York that has higher electricity costs, like 16 cents per kilowatt hour. So what you can get, and this is with electricity at 8 cents per kilowatt hour, we can look at the cost to purchase lamp 1, that HPS, versus lamp 2, that LED, in dollars per square feet. Then we see the electricity cost of lamp 1 versus lamp 2. So per square foot, we have about 80 cents less per square foot electricity cost for that LED fixture, but they cost more to purchase upfront. So our simple payback would be we'd have to operate those LEDs for 9 years to see a payback from that increased capital cost. However, if we're in a place where electricity is more expensive, so let's say 16 cents per kilowatt hour, because of the savings that we get for electricity from LEDs, in this scenario, the simple payback now goes down to 4.6 years, which is starting to get closer to reality. I think most growers I talk to want a payback for their things they install of 1 to 3 years. So 4 years would be a little bit long. So you can go through and do these for your own type of lamp specifications for your operation. One of the lighting tools that we linked to was actually not developed by Project Lamp, but developed by Jim Faust at Clemson University, and that's these daily light integral maps. And you can link to those, and there's a tool where you can pinpoint your location on the map or put in your zip code, and it will tell you by month of the year your average daily light integral at your location. Okay, so that was the material that I wanted to cover. Just to point out some upcoming webinars. So with Project LAMP, and you can go to hortlamp.uga to learn more. Our next webinar is going to be presented by Josh Craver from Colorado State University on end-of-day lighting strategies for greenhouse crop production. And then 3 other folks coming up after him every few weeks and through July 30th. And then we do have one other webinar I want to alert you to. So GLAZE, the Greenhouse Lighting and Systems Engineering Consortium, they have monthly webinars. And on May 16th, they're hosting 5 of our grad students that came out of Project LAMP that are going to be doing lightning talks, talking about their own research. So that's going to be very fast paced. I think we have 6 minutes per presenter, if I did my math right, and talking about light spectrum and environmental effects of LEDs, the interaction of far red and temperature, and the interaction of far red light and daily light integral. So do check that one out as well. So with that, I want to stop here and thank you for joining us today, and let me know if you have any questions.
Thank you, Neil. Very, very interesting presentation. Yes, if somebody has any question, feel free to ask here or send us a message to the chat as well.
Perfect.
I do have a question.
Yeah, go ahead, Renita.
Yeah, tell me more about the clothing that you were wearing, in the last picture.
Right. So this is good. This is a greenhouse that I visited in Leamington, Ontario, where they produce a lot of greenhouse vegetables. I believe this one was a cucumber producer. And so they have pretty strict kind of sanitary requirements for entering that greenhouse. They want to make sure that I'm not tracking in pests and diseases and food safety organisms. So here I am suited up, covering my shoes and wearing this Tyvek suit. And I think before this picture was taken, I was also wearing gloves as well.
I bet it was nice
yeah.
to see you wearing that news. I have a more generic question. So great presentation. I do think those calculators are there to be used, and hopefully, the people that attended here will use and spread the word about them. So one question that I received from my associate in research recently was something kind of puzzling. So we are moving towards LED lights due to many advantages. However, the college, for example, here, is not seeing any advantage on reduction in light use because we are replacing HPS lights by LED lights.
Mm-hmm.
And the majority of the conversion, had been done by replacing fixtures with the same wattage. For example,
Right. So then you're going to get higher intensity light, but
Mhm.
not necessarily save energy per greenhouse. And we
Absolutely.
we have the same situation at Cornell, actually. And so then in that case, we're not saving energy per greenhouse, but our researchers that use that space can get quicker crop turns. So for example, I'll just make up a hypothetical example, but our plant breeder with corn, like maybe previously it took them 4.5 months to get through a generation of corn from seed to seed. Maybe now they can get through that in 3.5 months or 3 months. And so we're not like selling product like per kilogram, like heads of lettuce or something like that. However, we can get through research trials more quickly. And so in that way, we can be more efficient in that space. So we somehow have to, in the commercial world, then we think about like how many kilowatt hours of electricity did it take per pound of tomatoes or per kilo of tomatoes. And LEDs will give us that. But then in a research perspective, yeah, it's like what does efficiency mean? And so it means getting through trials more quickly, for example, or having higher quality plants in trials, so that you can get better results. So that might help a college be ultimately get away with less greenhouse space, but have the same research output. Does
Yeah,
that make sense?
no, absolutely. Yeah, great point in there. So I believe that idea should, also be brought up to the attention of whoever is using these calculators, because at the end of the day, so we are basically talking about the same wattage with more efficiency. So there are other very positive impacts of, using LED lights in production other than just, a one-to-one replacement.
Yes, exactly. Right. So the tools are more for the commercial world, but when we get into those research examples, then reach out to researchers like us and me and help you figure out what is the value proposition for a lighting system.
Any more questions?
Hi, Neil.
Hey, Amanda, nice to see you.
Nice to see you guys.
Mhm.
Well, congratulations for the presentation. I was just listening to have a refresh in my mind.
Mhm.
And that got me thinking if you guys have any tools for comparing like LEDs to the dimmable LED lights.
Ooh, right. So I would say we don't have like online tools with that, but some of the benefits. So I've done research with these dimmable LEDs versus on-off LEDs is we can complement the sun, so that if the sunlight gives us a moderate amount of light, but we still need more, maybe we have, let's say, we'll make up a hypothetical example. Maybe our target light intensity is 300 micromoles per meter square per second, and our lamps could give us that. But let's say the sun at this point in time is giving us 200 micromoles. So then I could turn on those LEDs and give me only 100 micromoles of light. And I'm not kind of overshooting the crop target. So we found in studies with fruiting crops, we've seen some yield benefits of using dimmable fixtures. But we haven't looked at, I guess your question is more like the economics, like is it worth the extra cost of having
Right.
those dimmable fixtures?
Because I know that I guess I don't know, I just assume that they're more expensive up front than the regular.
Right. They tend to be a little bit more expensive up front. One nice thing that we know with LEDs, though, is that energy efficiency does not go down as you dim them, versus like high pressure sodium lights. It's not common that people could dim them, but some were dimmable, and you actually lost energy efficiency when you dimmed them. For LEDs, they actually get a little bit more energy efficient if you underdrive them instead. So if you dim them. So I think you'll see a tiny bit of energy efficiency improvement with dimming. But then I think in the end, what you'll see is like a crop quality and hopefully like yield effect of having like the same daily light integral stretched out across more hours of the day, so that you're not at those like peaks of photosynthesis. Yeah.
Well, thank you again.
Yeah, great question, and nice to see you.
Nice to see you too.
Okay. So just a
All
quick
right.
announcement, we will share the recording afterwards in our website for the project. Yes, thank you so much again, Neil. Very
All
good
right.
presentation.
Thanks for hosting me, Jorge. Have a good day, everyone. Take
All
care.
right.